So now that we've spent some time understanding upper and lower bounds for functions, let's talk about type bounds. So type bounds we didn't really do in our overview picture of stuff. So let's try to visualize this. So consider you have maybe two functions. You have a x to the fourth and x to the fourth plus 2x. So I've graphed that here in this picture. The one that starts more kind of linearly, right? This is going to be our x to the fourth plus 2x. The one on the other side is going to be x to the fourth. So I have two functions there. Notice that when x is reasonably large, these functions overlap one another. So they kind of follow each other one-to-one, right? Instead of one being substantially greater than the other or substantially less than the other, they kind of just seem to overlap. They exactly follow one another. This is what I would call a type bound. So the type bound of x to the fourth plus 2x is x to the fourth. As x gets really large, these functions become identical. Okay, so this is what's called a type bound. So there's just this kind of little area in the beginning, right, where that 2x has a little impact, right? But once x gets sufficiently large, right, gets past that, x0 cutoff point, right, they become effectively the same. So one thought would be, right, is that, hey, this is another way basically to model or to understand growth functions. We can hope to write a type bound for it instead of an upper bound or a lower bound. And this particular type bound, generally speaking, is going to give me a pretty good estimate for exactly how much work I have to do. Now, it will be a little bit off because I'm forgetting about that plus 2x term there, but for very large values of x, it'll be exactly the same, right? So type bounds are very nice when we can find them. They'll let us almost exactly model how our program behaves. So there are a couple different ways that we can write type bounds. We're going to introduce first tilde and then on the next page theta. So tilde. We'll literally write the following. We'll write tilde f of n, right, to basically represent a function that is type bounded. What the type bound means is basically, okay, if I have two functions, right, f of n, g of n, and I divide them, right, in the limit, that the ratio will be 1, right? So as n gets really large, right, imagine we're taking the limit, right, and we'll use the limit syntax down below. As that n value gets really large, right, that ratio is 1, right? And what that represents is that those functions are convergent on one another. They're basically overlapping on our graph, right? They are effectively the same, right? They're a type bound of one another, right? F is type bounded by G. Okay, so how do we actually find a tilde, right? How do we find this bound? Well, if we have a growth of n, it's actually, if we have a growth function, it's actually really easy. For a growth function, all we do is drop all but the dominant terms. So it's actually less work than trying to write one for a big O expression, right? In big O, we dropped all but the dominant term and then we dropped the coefficient. Here we leave the coefficient in place. Okay, so looking down, we actually have some examples. So here I have my f of n, and these are actually the same as what we did for big O. So we have 2n plus 3 as our first one. Well, in this case, I'm trying to find out what the tilde is, right? What is the type bound for it? I drop all but the lower term, I keep the dominant term and drop everything else. So in this case, I keep 2n. So this over here is saying that g of n, right, our type bound is equal to 2n. So type bound over here, original function over here. Now, if I want to validate that, right, I have to basically take a limit. Before we did some algebra, we had to figure out some constants. Here it's almost easier depending on how hard it is for you to evaluate a limit. Basically what happens is we need to check the ratio of them, right? So the ratio of g of n over f of n, right? Here I'm saying the limit of 2n over 2n plus 3. Of course, I'm taking the limit as n gets really large, right? We said earlier that we want to take a look at our programs, right, our growth functions when n is really large, right? For programs that are so large that there's no kind of special behavior happening as we kind of go between small n's, right? No special overhead, no special cases. So let n be really large. Now we do, right, so we want to, let's say, right, we've used that process basically to determine that g of n, right? Here we've said, okay, that g of n, right, the tilde, the type bound, is 2n. In order to verify that, right, all I really do, right, is take that limit of the ratio and evaluate it, right? So I take that there, and I see if it's what it's equal to. If it's equal to 1, then I'm good, right? Those things follow each other exactly in the limit, so that is a valid type bound. So here I'm not going to work through the algebra doing that. It's pretty simple, though. I really wouldn't expect you to do the algebra yourself either. As long as you set it up, you can probably put into something like a CAS, right, a computer algebra system, and it'll compute the answer for you. So our second example here, right, is for F2. F2 is a little bit more complicated. So this is log of n times 35 n squared. If we want to find the tilde for that, we drop all but the dominant term and then leave that term alone. So here, right, we drop this. Over here we had dropped the 3, and we're just left with 2n. Here we don't have a coefficient, so it doesn't really, there's no extra kind of information that we keep, right, by leaving it alone, right? Versus big O is throwing away that coefficient. Here, in tilde, we keep it, but if there's not a coefficient, well, it doesn't really matter. Again, if I want to show whether or not that's valid, I basically need to take the limit, right, as n approaches infinity of the ratio of those two functions. If it's equal to 1, then I'm good to go. And these two limits here, right, if you want to evaluate them, they will work out, right? They will evaluate to 1, so we should be good to go. So there we have it. So that's our kind of our tilde bounds for both f1 and f2. At this point, we have several different ways to characterize a function in terms of bounds, or in terms of asymptotics. My general preference is going to be for tilde. At least in terms of big O. So big O, right, was an upper bound, but big O, we were basically throwing away information, right? We threw away not just all the lower terms, but the coefficients as well. Tilde is keeping that information, right? Tilde is retaining that number in front, and that is really valuable because that number could actually matter, right? We can imagine that we have two functions. Maybe we have an f of n 1 over n versus f of n 1 of n. Those two functions in terms of big O of n, in terms of big O, are going to look the same, right? They're both going to be O of n, right? So if I have here, let me actually just draw this. So I have, an f of n equal 100n, right? And f of n equal, say, 2n, right? In terms of big O, these things are the same, right? These are both going to be big O of n. This basically is throwing away the fact that one of them is 50 times slower than the other. I don't like that. In tilde, right, we would have maybe tilde of 100n versus tilde of 2n, right? We keep the coefficient. In that case, I can clearly see how different those things are. And so for me, right, I prefer that tilde because I'm not throwing away information. The only issue, right, is that tildes can be harder to write because you need to have that coefficient in front. If you think back to some of the empirical analysis stuff we did, we may have an A value, right? We may have a value in front, but it's kind of questionable, right? Maybe it's super specific to the system or something. But if we have it, right, I really think we should keep it. Now, as a final note here, I kind of have another kind of remark here, right, based on big O. So here, right, we're saying we gave a pros, right, for determining the g of n in a tilde. Now, g of n, right, is literally just a term from the original growth function, right? It's a particular mathematical term. What we can think of is the following, right? My f of n, right, my original function, like this over here, right? That is really g of n, right, the type bound, right, that first term, plus some error, right? So tilde, we say throw away all but the dominant term, right? So in this case, right, my dominant term is linear, right? It just has n in it, versus my other term is constant time. Well, basically what that means, right, is we can say, think of this as, f of n is g of n, right, or 2n, plus some error, right, plus O of 1 error, right? So O of 1 is basically a little quantity that kind of can vary a little bit. Basically what we're saying is that the error in that expression is upper bounded on some constant. That may be a little bit awkward to think about, but big O really, when we write it in a mathematical expression, we won't do it often in this course. Usually we just set it equal to f of n to say, this f of n is bounded by something. But when we use O of n by itself, what that's representing is a little bit of a term that can fluctuate, right? So in our tilde expression, right, we threw away that constant, right, our term that wasn't dominant. And really, right, in practice it was a 3, but we just threw it out. And the way we can represent that we threw that out is by saying that it's there's an O of 1 error there, right? I'm using the word error basically whenever I have O of n in a normal expression to represent that O of n, is this kind of a bound, right? There's tons of things that could be under it, right? Upper bound is basically representing that I have this mystery function that hides underneath it. Here, right, I could be hiding a 4 or 5 or 6, right? I threw away whatever constant was added on there, so it could have been any of those. And the way I can represent that is actually using big O. The next line there, I have a similar example where I said f of actually it should be f2, right? That thing is really g2 plus an error on log, right? Log of n. Because I kept the dominant term and then I threw away the log term. So that gives me a little bit of error. Okay, so let's take a look at some more. Okay, so tilde is rather nice because it keeps a lot of detail. Maybe you don't have to worry too much about that relationship with big O, but just know that it contains more information. It's a tighter bound. Now let's take a look at one more method we can use to tightly bound something, and that's called theta. So theta goes back to our definitions of big O and omega. So basically what we say is that a function is type bounded by g of n, right? So we have this over here, f of n. F of n is type bounded by g of n, right? It's theta of g of n when, and this holds, f of n equals theta of g of n, right? If and only if f of n is big O of g of n and f of n is omega of g of n. Right? So when our upper bound and our lower bound are the same, well then my theta holds. Now the issue here is that it's rather hard to get both upper and lower bounds to look the same. Right? So if you think about what we've talked through, you can think about, maybe our upper bounds are going to look something like n, our lower bounds are going to look something like 10. It's hard to make those converge. So a lot of times our thetas don't really exist because they require us somehow to bring our kind of our upper and lower bounds together. So if I do think about this graphically, right, normally I have something like this, where this is maybe my f of n, this is my upper bound, I'll call it a, my lower bound, I'll call that b. And the problem is, right, is that normally a and b diverge. Right, those functions go their own way. Sure, a is an upper bound for f, b is a lower bound for f, but a and b don't ever, kind of meet up again. They diverge. The problem, right, with this definition is that basically it's saying that you have to basically bring these in, right? And so it's going to be extra work for you basically to prove that our O of n and omega are really close together, right? That they are the same. And only once you've done that, right, once you basically brought in those two functions, right, made them as tight as possible, get them as close to f of n as possible, are you allowed to say that f of n has a type bound that's equal to a and b, right? That those kind of, they compress together, right, on that line, and once they meet up, they enforce a type bound, right? They enforce the theta bound. So this is a little bit harder to do than some other things. Again, this is going to be something we almost never use. Just think of it, for us, what we think of it as for us, the way we think of it is that theta is simply a type bound, right? So it's another function that closely follows a growth function. For us, though, we'll mainly use tilde just because it's going to be a little bit easier to write, a little bit easier to think about. Theta is more popular in literature. It's maybe something you hear people talking about, but it's just so hard to get.